Oxidation number. As already discussed, oxidation reduction reaction involve the transfer of electrons from one atom or ion to the other. In case of ionic reactions, it is very easy to determine the total number of electrons transferred from one atom or ion to the other. However, in many redox reactions involving covalent compounds, it is not so easy to determine the direction of transfer of electrons and number of electrons transferred from one reactant to the other simply by looking at the chemical equations. For example, in the following redox reactions, 2H2 gas plus O2 gas arrow 2H2L stands for liquid. So both the reactants and the product are covalent compounds. From our knowledge of chemical bonding, we know that during the formation of H2 molecule, an electron pair is shared between each hydrogen and oxygen atom, and the electron is not completely transferred from hydrogen to oxygen atom. Yet in H2O, oxygen atom and that electron is not completely transferred from hydrogen to oxygen atom. Yet in H2O, molecule O atom has higher electron density and thus there is a partial transfer of electronic charge, better called as electron shift from hydrogen to oxygen. In other words, we can easily say that hydrogen is oxidized and oxygen is reduced. What is said about the reaction between H2 and O2 may be true for a number of other reactions involving covalent compounds. Two such reactions are H2 plus Cl2, 2HCl, then CH4 plus 4Cl2, CCl4 plus 4HCl. In this reaction, H2 and CH4 act as a reducing agent while Cl2 act as an oxidizing agent. With a view to identifying oxidizing and reducing agent by keeping track of number of electrons transferred from one reactant to the other, both in ionic and covalent compounds, and to help in balancing of equations, the concept of oxidation number was introduced. Thus, oxidation number of an element may be defined as the charge which an atom of the element has in its ion or appear to have when present in the combined state with other atoms. Oxidation numbers are also called oxidation state. Now, let us discuss the rules for assigning oxidation numbers. The following rules are applied to determine the oxidation number of an atom in an ion or molecule. The oxidation number of all the atoms of different elements in their respective elementary states and allotropic forms is taken to be 0. For example, N2, Cl2, H2, He, P4, S8, O2, O3, C, diamond or graphite, Br2, Na, Fe, Ag, etc. The oxidation number of each atom is 0. Next, the oxidation number of a monoatomic ion is the same as the charge on it. For example, oxidation number of Na plus, Mg2 plus, and Al3 plus ions are plus 1, plus 1, plus 2, plus 2, and plus 3 respectively are their oxidation states or oxidation number, while those of Cl negative, S2 negative and N3 negative ions are -1, -2 and -3 respectively, as indicated here. -1 single, 2 negative, 3 negative oxidation numbers. These are the oxidation number of these particular ions. Next, the oxidation number of hydrogen is +1 when combined with non-metals and is -1 when combined with active metals called metal hydrides such as LiH, KH, MgH2, CaH2, etc. The oxidation number of oxygen is -2 in most of its compounds except in peroxides like H2O2, BaO2, etc., where it is -1. Other interesting exceptions are found in the compounds OF2, oxygen difluoride, and O2F2 dioxygen dichloride, where the oxidation number of oxygen are +2 and +1 respectively. This is due to the fact that fluorine, being the most electronegative element known, has always an oxidation number of -1. In compounds formed by union of metals with non-metals, the metal atoms will have positive oxidation number and the non-metals will have negative oxidation numbers. For example, the oxidation number of alkali metals Li, Na, K, etc. is always +1, and those of alkaline earth metals Be, Mg, Ca, etc. is +2. The oxidation number of halogens F, Cl, Br, I is always -1. In metal halides such as Kf, AlCl3, MgBr2, CdI2, etc. In compounds formed by the union of different elements, the more electronegative atom will have negative oxidation number, whereas the less electronegative atom will have positive oxidation number. For example, first, N is given an oxidation number of -3 when it is bonded to less electronegative atom as NH3, and Ni3, but is given an oxidation number of +3 when it is bonded to more electronegative atoms as in NF3. Since fluorine is the most electronegative element known, so its oxidation number is always -1 in its compounds, that is oxides, interhalogens compounds, etc. In interhalogen compounds of F, Cl, Br and I, the more electronegative of two halogens gets the oxidation number of -1. For example, in IF7, the oxidation number of F is -1 while that of I is +7. Similarly, in BrCl3, the oxidation number of Cl is -1 while that of Br is +3. In neutral compounds, the sum of the oxidation number of all the atoms is 0. In complex ions, the sum of oxidation numbers of all the atoms in the ion is equal to the charge on the ion. In polyatomic ions, the algebraic sum of the oxidation number of all the atoms in the ions is equal to the charge on the ion. For example, the sum of oxidation numbers of all the 3 oxygen atoms and 1 carbon atom in the carbonate ion CO3, 2 negative, is -2. The term, a term which is more oftenly used for oxidation number, is oxidation state. For example, in CO2, the oxidation state as well as the oxidation number of carbon is +4, while the oxidation state or oxidation number of oxygen is -2. This means that the oxidation number denotes the oxidation state of an element in a compound. Metals invariably have positive oxidation states, while non-metals may have positive or negative oxidation states. Transition metals usually display several oxidation states. The highest positive oxidation state for S block element is equal to its group number, but for P block element it is equal to group number -10, except for noble gases. However, the highest negative oxidation state for P block element is equal to 8 minus the number of electrons in the valence shell. In other words, the highest positive oxidation state increases across period and the predictable. For example, in the third period, the highest positive oxidation state number increases from +1 to +7 as shown. Group 1, Group 2, 13, 14, 15, 16 and 17. Elements: Group 1, Na, compound NaCl, oxidation state of the underlying element in the compound. Oxidation state of Na is +1. Next, Group 2, element Mg, magnesium, compound MgSO4, so oxidation state of this one, magnesium, +2. Same in all these. Al, AlF3, +3. Al, oxidation number or oxidation state, +3. Next, Si, Cl4, +4. Next, P, PF5, PF5, P plus 5, P4O10. Again oxidation number is plus 5 or oxidation state is plus 5. S, SF6, S plus 6 oxidation state for S, sulfur. SO3, oxidation state of S plus 6. Next, Cl, chlorine. HClO4, Cl plus 7, Cl2O7, Cl plus 7. We shall now illustrate the use of above rules in determining the oxidation numbers and also for identifying the reductants and oxidants in redox reaction. Thank you.